So, today we will cover tutorial 2. In the first tutorial, Pritam has covered n-gram language modeling. So, today I will cover some of the basic tutorial for the deep neural network and gradient descent, backpropagation, and I will take a simple neural network and I will let you understand how everything works together. Okay. So, throughout this lecture I will just take this simple deep neural network where we have only two inputs I1 I2 and there is two hidden units only H1 H2 and there are two output units O1 and O2. So, I have already manually given some of the input values and some of the weights. So, we will understand each of these things just after some time. So, before going to the depth of this deep neural network, first I will talk about little bit about the activation functions. So, there are many activation functions just to introduce some of the non-linearity in the deep neural network. So, first let us import some of the required libraries. So, for this tutorial you need only two libraries, one is the NumPy, another is the matplotlib. So, you can import like this. So, first I will talk about sigmoid activation functions. So, as you can see this sigmoid function is taking input as x and it is returning 1 over 1 plus e to the power minus x. This is simple sigmoid activation functions. So, this function generally used in binary classification for logistic regression tasks most of the time. So, for this tutorial I have taken some of the values from minus 10 to 10 range as you can see in this graph, and just I am passing this sigmoid, calling these sigmoid functions, taking some values which are linearly distributed and the values should come from the range minus 10 to 10. And in order to plot this function you can simply call plt.figure from the matplotlib library. Then I have given some of the axis label like this is the input and this is the output. So, if x is your input, your output should be 1 divided by 1 plus e power minus x, that is the sigmoid function, and this function looks like this. Now, let us talk about the tan hyperbolic activation function. So, similarly you can write tan hyperbolic function where given the input x you will return tan hyperbolic of that x. So, if I try to run this, so for all of these activation functions I have taken this x input as constant, like this will come from the linearly distributed which is come from minus 10 to 10. Okay. So, as you can see we are getting some error because previously I have not run that cell, for that reason it is showing x is not defined, but now I have already I have defined x. Now, let us see how tan hyperbolic function looks like. So, it looks like this. Next, you have already understood the ReLU activation functions. This is most of the time in the hidden units in the deep neural network it is being used. So, what it does, given a value of x, it will just take the maximum between 0 and x. So, as you can see this ReLU function, so it is returning, taking the value x, it is returning maximum between 0 and x. So, if you give value as 0 and let us say if your value x is 1, then it will return 1. Now, if I just want to plot this function, it will look like this. So, as you can see from minus 10 to 10, when the input is from minus 10 to 10, as you can see you are always getting the value as 0, because anything negative comma 0, the maximum between this negative and 0 will always be 0. So, as you can see from minus 10 to 10 we are always getting output as 0, but once the value becoming positive, that is from 0 to 10, we are getting that particular value only, right. So, this is the ReLU activation function. So, there is slightly modified version of the ReLU, that is called leaky ReLU activation functions, where what we does, if the value is greater than 0, we will return x, otherwise we will do alpha into x. So, alpha is your some hyperparameter. So, where in this example I have taken alpha is the 0.01. So, as you can see, so this leaky ReLU activation functions also look like this, looks like ReLU only with some modified version, because we are just multiplying that x with alpha. And the last activation function I want to talk about, that is the softmax activation functions. So, these activation functions are popular for the reason I am covering in this tutorial. There might be some other activation function also. So, sigmoid activation function, as you can see, given the value input as x, we are getting, first we are doing exponential of x minus np dot max x. So, this is the softmax function. So, we have introduced this for the numerical stability, for the reason we have implemented like this. Now, if I want to run this look like this softmax activation functions. So, your input is constant like minus 10 to 10, and we are getting output like this. Now, here I have compared all of the activation functions that I have talked about. So, sigmoid, this is generally used in binary classification task, and tan hyperbolic function, it is centered at 0 and useful for hidden layers in certain tasks. And the ReLU activation function, that is most of the time default for hidden layers in deep neural networks due to its simplicity and the efficiency as well. Leaky ReLU is the variant of the ReLU function, which addresses the dying ReLU problem. So, in the ReLU activation functions, you have some problem called dying ReLU problem. And the softmax, it converts the output, whatever output you are getting at the output layer, to some probability distributions, and this is most of the time used for multi-class classifications or some task where you need some probability distributions over the output. So, if you plot all the activation function together, you will get a plot like this. So, each of the activation function is color coded with different color, you can visualize this. So, this I talked about little bit about just to introduce you for some of the activation functions, how you can plot everything and how each of the shape looks like. There is so each of the activation functions. So, you can introduce any of the non-linearity, but these are the popular activation functions. I will go slowly. So, first I have covered the activation functions. Now, I want to cover the basics of gradient descent, because in order to understand the basic deep neural network, you need these components to be clear. So, here also I need those two libraries, which is very simple, NumPy and the matplotlib. So, here I have taken a very simple loss function, which is, let us say y equal to x square is your loss function. So, in your class you have already known that there is some loss function called mean square error loss function, but for the simplicity, just to understand this, I have just taken a simple loss function where given the value x, the loss is x square, y equals to x square. So, as you know, in order to calculate gradient descent, gradient means the derivative. So, initially we have calculated the derivative of that loss functions. So, as you know, if I make a derivative of x square, you will get 2 x. For the reason, in the gradient function I am returning 2 into x. Now, you already know in the gradient descent, each of the step you have to update something. So, you have started with some initial value, let us that initial value is old, and now you want to update that value depending on the gradient descent, right. So, your new value will be whatever old was. So, old minus you introduce some of the learning rate into your slope, slope is nothing but the gradient. So, every time new will be updated as new equals to old minus learning rate into slope. So, I just want to implement this function. So, here I have not introduced any of the torch library or something, by simply NumPy you can easily implement the gradient descent algorithm. Now, if you understand this function, so this is gradient descent functions. So, what we need a starting point, because you have to start with something and you need some learning rate, how faster or slower you want to update that value. and you need iterations, how many iterations you want to do. Then I am just doing x equals to the starting point. So, you are starting with some initial value that you can randomly initialize. So, there are different initialization method also, like there are some other method also like Adam, momentum, there are many algorithms, but you can start with some initial value. And let us say I am taking history as an array just to take into account what are the loss I am getting for each of the steps. Now, I am just looping over all the iterations. So, for I in range iterations I am just calculating this loss functions. So, loss function you already know, this is the y equals to x square, right. I have already mentioned loss functions returning x into x square. So, for each of the iteration you are calculating the loss, now you are calculating the gradient also, right. So, your gradient is gradient of x. Then in the history array I am just appending both x and the loss as well. So, if I just run this, so let us say I have started with the value 10 and let us say I have taken a learning rate 0.1, right, and for simplicity let us say I have taken only 50 iterations. So, these are the 3 variables required for your gradient descent algorithm. Now, let us run it. So, if I run it, you can see for each of the iterations I am just taking what is the value of x, what is the loss and what is the gradient. As you can see in the first iteration x, I have started with initial value as 10. Now, the loss you are getting x square, right, which is 100, and the gradient is nothing but derivative of x square, which is 2x, that is only 20. And iteration 2, how I should update? New equals to old minus learning rate into slope. So, in this iteration what it will be, previously it was 10, then 10 minus learning rate is 0.1 into gradient. So, 0.1 into 20 it is 2. So, 10 minus 2 your at the next iteration x will be 8, then loss will be 8 square 64, then again you will calculate the gradient which is 2 into 8 is 16. Like that I have done for 50 iterations, right. As you can see the loss is becoming lower, right, from 100 to, as you can see, I have reached to almost 0 at the iteration number 34, right. So, after 50 iterations I am getting the new updated value of x as 0.002 and loss is 0, right. Let us visualize this. So, just to visualize I just wrote a simple script. So, you have in the history you already have all the x values and the loss values, because in the history I have in that array I have already appended those 2 values just to keep track of how the loss is changing according to the x. Now, I am just trying to plot that loss functions. See, it looks fantastic, right. So, in the x axis I am just taking value of the x. Now, I have started with the value 10, as you can see. So, this rate point on top, then in the next iteration you know we are getting some value around 8. So, which is right there. Now, at each iteration see we are descending with respect to the gradient. So, we have to achieve to the minimum. So, in this graph the minima is at 0.0, right. So, we started with 10 and initially we have updated in such a way that we achieved the minima through the gradient descent algorithm. So, this is simple gradient descent steps. And if your loss function is something more complex, let us say 2x square minus 2 or some quadratic other loss functions, the gradient descent algorithm will work in the same way, but this is very simple fundamental. Now, if you want to play with some different learning rate or different starting point, let us do that once. So, if I could have start with, instead of 10, if I could have start with 5, keeping the same learning rate, let us see what would happen. Now let us say I do not want to iterate for 50 iterations, because I already know lower with less than 50 iterations I can reach to the minimum. Let us do it 20. So, I have changed the starting point 10 to 5, I have changed the number of iteration 50 to 20. Now, let us run it. As you can see, I am getting this figure like this, right. Now you can play with different things. Let us say I am starting with same 10, right, and let us say I am doing 50 iterations only, and let us say I am just doing learning rate as instead of 0.1, let me lower the value, let us say 0.01. So, it will be updated slowly, right. I have just reduced the learning rate. Now, let us see. So, as you can see, in the next iteration, previously when the learning rate was 0.1, at the time iteration 2 we are getting x equals to 8, but now we are getting 9.8. See, the value of x is very slowly decreasing, right, and as you can see in the previously at the iteration 34 we are getting loss equals to almost 0, but here at the iteration 50 also we are getting loss as 13.8088. So, here we have to increase the number of iterations. You can visualize these things how it looks like, but I will try to increase the iteration. As you can see here in the gradient descent step, it is slowly updating, but it is not achieving the minima, because minima is at 0, because I have stopped at the iteration number 50. So, let us increase this number of iterations to 50 to 100. Now, as you can see at the iteration 100 we are getting loss as 1.8313, lower than the previous, but still we may not get the minima. We may have to increase the number of iterations more. So, let us do 200. So, other than that, it is better there to choose good learning rate, not very higher, not very lower. As you can see, with 0.1 only we could achieve the minima at the iteration number 34, but now I have changed it to 200, I have increased to 200. Let us see what happens. Now, you see at the time of iteration 200 we are getting loss as 0.0322, it is still not 0, but it is closer to 0, right. So, it is closer to 0. So, you can play with this. So, let me just try once more, let us update 200 to 250, or let us do 300. So, at the time of iteration 300 we are getting 0.00006. So, it is very close to 0 now, right, we are getting 0.0. Instead, if you keep 200 iterations and let us, if I do instead of 0.01, if I could do let us say 0.08, see, then we are getting 0. So, in that case we are getting 0, if I could check correctly at the iteration number. So, when we get the first 0, right, see, there we get at the iteration number 43, right, because 0.08 very closer to 0.1. Initially we started with 0.1 where we achieved the minima at iteration number 34. So, now we are getting at iteration number 43. Good. So, let us visualize this. Yeah. Okay. So, you can play with these numbers. Okay. Now, so I have started with taking a simple deep neural network, right. So, just a minute, let me copy that thing here just to understand it better. So, from now onwards I will take this simple neural network and I will just let you know how you can implement this neural network in by using Torch library. Okay. but here I will just teach you one interesting thing. So, here I will just teach you how you can manually give the weightage in the torch library. Okay, just a minute, sorry, I have to do it text. Yeah, so I will take this simple neural network. As you can see, there is only two input I1, I2 and two hidden layer H1, H2 and two output O1, O2. So, you have already understood gradient descent, you have already understood the activations functions. So, these two things require. So, at the time of back propagations, it uses the gradient descent algorithm. So, there is something called forward pass. So, you go from left to right and you calculate some of the error or loss. Then once you calculate the loss, you just want to back propagate just to minimize this loss. And in this process, when you are just going from right to left, that is you are back propagating from output to again input, at the time you are updating some of the weights which you have started with. And how you are updating, that you have already learned through gradient descent algorithm. So, you have to adjust the weights in such a way that your loss will be minimum. In that way, you will get better output. So, you can start with some random weights. So, for this exercise, I have taken, let us say, so from I1 there is two weights, right, W1, and from I2 there is going W2, and from I1 another weight W3, and from I2 W4. So, there are 4 weights because we have 2 inputs and 2 hidden layers. So, 2 into 2 we will have 4 weights. So, manually I have chosen W1 as 0.15, W2 0.20, W3 0.25 and W4 0.330, and I have taken a bias, which is I have taken a bias. Okay. Now, from H1 to O1, that weight is W5, W6, W7, W8. So, from the hidden layer to output layer in that second layer, so we have chosen some of the manual weights. So, there also we have chosen another bias input B2. Okay. And I1, I2 we have taken as 0.05 and 0.10. So, this is the simple thing I have taken. Now, in order to implement in torch, so you can import these libraries like import torch.nnh nn. So, nn is nothing but neural network. So, you do not need this because I have already imported torch, you do not need this. So, this also I have imported. Now, so if you do simply two question marks followed by, let us say, nn dot linear. So, for any functions, if you want to understand the signature of that functions, you can take the help like this. You can see the signature, right. So, this nn dot linear, which is a linear layer, which does what it does? It just linearly transforms some of the values. So, y equals to A transpose x plus b, right, and you can get the whole informations. So, if you do not know anything about some of the package, you can simply put a two question marks, then followed by you can define whatever package you want to know. For an ended linear, you can do like this. Now, how you can use this? So, in the signature also sometime you can get the sample example also. You can see m equals to nn dot linear. Then how you can pass some of the input to that linear layer? You can define some of the input and you can call that nn dot linear like this. So, let us do this exercise. So, let us say I am choosing nn dot linear 20, 30. So, here what it contains? First one is contains the input features and next in because the out features. So, let us choose 20, 30, and you can, if you do simply nn dot linear, you will simply get the whole signature also. So, for an example, let us say if I do m equals to nn dot linear 2, 3, then and I am let us say doing some input. So, randomly I am selecting some of the input 3, 2. So, if my input is like this, right, there is 2 features for each of the input and I have 3 such inputs. And for the output, what you can do? You can pass this input to the linear layer, right. It will be simply multiplication of your input and whatever input that you can and some of the weights. Yeah. and you can simply get output dot shape 3 comma 3, because you are multiplying a matrix 3 cross 2 and another matrix 2 cross 3, then essentially you will get 3 cross 3 output. And here whenever you apply some of the NN dot linear, it randomly initialize, the model randomly initialize that data. But if I want to put some of the if I want to put weights manually, you need to do something else. And how you can get what weights is applied, you can simply call m dot weight dot data, then you can get what are the weights it contains, 3 cross 2, right, 6 weights you get, and you can simply call m dot bias, then you can get the bias value also, right. But what I want to, the examples that I have shown, I want to put some of the weights manually. So, as you can see, I am just giving the weights manually. How you can give? So, you can simply call self dot linear dot weight dot data, then you can pass that weight. So, initially we had 0.15, you can see in the figure 0.15, 0.20, 0.25 and 0.30. So, these 4 inputs, this is the 4 weights that I am giving manually. Then I am just giving bias or data also, which is 0.35, as you can see in this example 0.35 bias, which is also a parameter. And in the second layer what we are giving 0.40, as you can see in this figure 0.40, 0.45, 0.50, 0.55 and the bias value is 0.6. So, if I want to give manual weight to the weight, then you can simply, this is your linear 2 layer, right. First one is the linear, then let us say I am defining linear 2, another linear layer which will be size of hidden layer comma output size, and in the first case you will giving the input to the first hidden layer. For the region, as you can see, the linear one is the input size comma h1, and in the next layer you have h1 comma output size. So, instead of 2 layer, like only one hidden layer and one output layer, if you would have 2 hidden layer, then you will have 3 things. First one would be input to hidden 1, then hidden 1 to hidden 2, then hidden 2 to output. So, here I have only 2. For the reason I am giving self dot linear 2 dot weight dot data. So, here I am passing 0.40, 0.45, 0.50, 0.55, and I am bias value I am passing 0.60. So, in this way you can manually also put the weight. If you do not put manually, the torch dot NN dot library function will automatically randomly initialize some of the weights, as you have seen in the earlier shell, which was randomly initialized. Now, let me run this. Okay. Now, once you initialize the weights, you have something called forward function. So, in the forward function what I am doing? I am just here I am using sigmoid activation function. So, we have already understood sigmoid activation functions. So, first it is passing to the linear layer, which is the simply weight transformation. So, whatever input is coming x, I am just passing to self dot linear layer. Once it is passed through the linear layer, then we do some non-linearity through some activation functions. Then whatever value you are getting, that is net underscore h, you are passing to that sigmoid activation function, you are getting out underscore h, right. And then once it is done, again we have another linear layer, right, that is hidden from output. Then you are just passing to that net o equals to self dot linear to out h. Then finally you are getting the output. Then again I have another sigmoid function which is passing taking the input of net underscore o. So, do not worry, I will just show the output of each of these things. So, now I have to, okay, so let me delete this one, it is not required. Okay. So, now I have to, let us say I am just initializing model as perceptron 2 comma 2 comma 1, right. So, this perceptron is taking, one is the input size, hidden and output size, right. Then if you want to check what are the model parameters are, you can get by model dot parameters. So, because I have given the weights manually and which was 0.15, 0.2, 0.25, 0.30, you can get this. So, first tensor is having the weightage in the first input to hidden layer, and next one is the bias which is 0.35, and the next one is the from hidden layer to output layer which is 0.40, 0.45, 0.50 and 0.55, and the last one is the 0.60. Okay. So, this is the bias value. Now, if I do the forward pass, after first forward pass you can check the what you are getting. So, you have to simply call model dot forward. So, when you are calling model dot forward, you have to give the input values, and you already know in this figure I have given input value as 0.05 and 0.10. You can simply call model dot forward, then you can get the first, see H1, H2, all the values I have printed. Then after the activation, sigmoid activation, you are getting out H1, out H2, then you are passing to the linear layer, you are getting net O1, net O2, then again you are passing through the sigmoid activation function, there you are getting out 1 and out 2, right. Great. Now, let us say I am just trying to use some MSE loss. So, now in this deep neural network, in this simple network, I just want to optimize mean square error loss, right. Okay. So, for this figure we had only two outputs, right. For the region previously I just wrongly defined, I think 2, 2, 1, but it will be 2 output layers. So, you can simply call 2, 2, 2, right. Then you can calculate total MSE error. So, this is after first forward pass you can calculate the error. So, error is this. Now, where you are getting the error, you have to do the backward pass. So, in the process of backward pass it will try to optimize the loss in through the gradient descent algorithm, right. So, in order to do the backward pass in the torch library, you can simply call first you have to define some of the optimizer, then you can simply call. So, here I have defined one of the optimizer, right, which is stochastic gradient descent. So, see SGD is the stochastic gradient descent and it is trying to optimize some of the criteria. So, here my criteria is MSE loss, you can see the criteria, right. Now, we are just first doing the gradient as the 0, then we are just trying to simply backward. So, this is simply loss dot backward, and after each of the backward step again you have to call something called optimizer dot step, then the whole process will again do. So, after trying to backward through the graph a second time, they are already been freed, saved immediately. Okay. Let me call one second. Yeah. So, you can do the loss dot backward, then you can again get the model dot parameters. As you can see, the model parameters got updated, right. So, previous one you can forget this error, because I think I have called loss dot backward twice. So, here you have to do optimizer dot 0 grad, then you can simply do loss dot backward. Okay. Then you can loop over through the models, you can take some more iterations, then you can run, you can get after each iterations you can check the output like this, because for after each iteration I have shown you what are the outputs. Then again finally you can check after all the iterations, you can check what is the very good model parameters just to optimize the loss. You can get the final value by again calling model dot parameters. Then if I want to predict some of the new values, let us say for 0.06, 0.12 value, what is the output, you can simply check this. So, first tensor, this is first output is getting 0.06 and 0.93. So, it will the probability is higher is 0.93. So, it will predict 1 like that. I think so far this is clear. So, I will end this tutorial here. So, I have covered the basic deep neural network and the gradient descent and the activation function.